and we can find its root and its eigenvector, where the poles, the roots are the poles of the system related to natural frequency, and eigenvectors are the modes of the system. I purposely wrote both the right eigenvector and left eigenvector. Left and right eigenvector will be the same if the MCK matrices are symmetric in nature. So we can write an eigenvalue equation for individual poles and or individual eigenvalues and corresponding eigenvectors. We can also represent in a modal and spectral matrix form. So this is called a spectral matrix. You can decompose this quadratic eigenvalue problem into this form, provided delta here is a diagonal matrix and V here is the matrices composed of all the 2n eigenvalues. Okay. This is the property of the quadratic eigenvalue problem. Now, if you look at Dr. Datta's book, and I believe in 80s, he has shown some of the orthogonal properties of this quadratic eigenvalue problem. One orthogonal property we have used in modal transformation, orthogonality of mode shape. There are some other relations based on M, C, and K. Note that I made a note. The P here, which he used here, these are the damping matrices. Just took it from his book. So he has proposed three orthogonality conditions of a quadratic eigenvalue problem. All three states that this form of decomposition will lead to diagonal matrices, and these diagonal matrices are related to each other. So let's look at one of them. This is the decomposition of a quadratic eigenvalue problem. These are the modal and spectral matrices, and I am going to show you prove that this indeed is diagonal for such decomposition. So we have the decomposition of the quadratic eigenvalue problem. I want to prove that this expression is diagonal. So from the given relationship, I can rearrange it to write terms of C matrix in the left hand side, and then pre-multiply by sigma B transpose, and then we have this expression. Then again I can take that transpose of this expression and then post multiply by B times sigma matrix. You know the transpose A times B transpose is B transpose times A. That's exactly what I'm doing. So what it will give us? It will give us two expressions which have the same left hand side, which means the right hand side is also equal. Now let's look at the right hand side. If you look at the right hand side of the matrices, which will now be equal, and we can rearrange it this form. Now, what kind of a matrix is this? Diagonal. And this is also diagonal. So if a matrix multiplied by a diagonal matrix can commute A times B equal to B times A, B is diagonal, then this must be diagonal. So we find out the orthogonality property of this quadratic decomposition. So similarly, if you find his book in the library, most probably you will have it. You can derive all the orthogonality properties. But this orthogonality property you will see then become the basis for deriving the condition of partial eigenvalue assignment problem. So now in partial pole assignment, the goal is that if we have 2n number of poles, I want to place m number of poles and retain the remaining open loop poles in the closed loop system. One thing you should know that when you develop a solution for partial pole assignments, it's a generalization of a full pole assignment. Because if m is equal to 2n, That's the complete pole assignment. Yes? So I have partitioned my system of the mode shape and the spectral matrices this way. And this is uh, the most celebrated paper in this area where Dr. Ram was my advisor, where they have shown that if you choose your feedback control gain F and G in this form, which means in order to design your control gain, you only need mass and stiffness matrices, which I talked about, that you can get it very accurately, even from finite element software. The modes and natural frequencies which or poles which you want to assign. First M1. So a very large system like aircraft wing, we are interested in controlling only 6 modes. I can find out first 6 natural frequency and corresponding modes from the experiment much easily than finding the 20th mode and 20th natural frequency. Okay? So it works very well because these things can be available from the experiment. So if F and G in such form and Q is a vector of dimension m by 1, then it can be shown that for any arbitrary vector Q, this expression will go to 0. What does this expression means? That all the contribution of the unaffected poles will go to 0 of the control system. So this is the condition of no spillover. You will make sure that the remaining pole of 2n minus m does not move. So in the closed loop system, these are also the poles of a closed loop system. And of course, these are the mode shape and spectrum of the open loop system, which we don't want to measure. So if we can prove that, I just have to have this information. Let's look at the proof. We want to make sure that this expression goes to 0. I just expanded. I put the definition of F and G here. Okay. And then from the previous relationship in the quadratic form, I substituted the expression for C here. And when you resolve it, you will end up having this term. Now, if this term has to go to 0, now if you look at this matrix form, you will have a diagonal terms which all the 1, and then you have a cross coupling term 1, 2, and 2, 1. Now, if you look at our orthogonality relationship, what it says, that this is diagonal. This is diagonal. Any off diagonal term has to be 0 from the orthogonality relationship. So that makes the entire system to be diagonal. So if this entire system has to be diagonal, then this must be 0. And that's how you can show that expression right hand goes to. And we prove that by choosing that form of F and G, there will be no spillover. Now the next step is, what is that Q, which will place the poles from lambdas 1 to lambda m to mu1 to mu2. So we ensure that form of control gains will show no spillover. So for the Q, they have given an explicit solution for the quadratic eigenvalue problem. This is your control distribution vector. These are the mode shapes which you want to change. Mu is the new eigenvalue you want to new poles which you want to place, and these are the old poles. So you need the information of the old poles and the new pole location. We always define what is the control distribution vector and the sum of the eigenvalues corresponding to the open loop poles we want to fix. So with this, once you compute this quantity Q, you can find out. So you have this formula, you ensure that you have moved the m number of poles and also ensures that there is no spillover for the remaining. They have also talked about that you may do the pole assignment, but the system may not be controllable. Now, when it will not be controllable? When this term goes to 0. When two vectors goes to 0, when they are orthogonal to each other. That's the case of also the case of uncontrollability. You want the system to be uncontrollable to take that to 0. So as long as they are not 0, your selection of P is such that it's not orthogonal to the eigenvector will be fine. So just a numerical example, you have M, C, and K. The P vector is given to you 1, 2, 0. These are the open loop eigenvalues. I want to change the first two eigenvalues without affecting next two. I have a formula to get. These are the first two natural frequencies, right, in a spectral matrix form, and these are the corresponding modes, 3 degree of freedom system. The first column is first mode, and then you have a formula in Q. I just expanded this because this is something I asked you to do for your take home also, right? Expanded this problem and given you just the aeroelastic problem, 2 degree of freedom, much smaller than this. You can calculate your Q1 and Q2. This is your Q vector. Once you have this Q vector, you can calculate F. Okay. Include this F and G, dynamics of a control system. You will find the first two poles have moved, the location you described, but the rest of the poles are still a part of the group. Any questions so far? It's just one formula which you need to implement. Now, I started working on this problem because I had to deal with aeroelastic problems, which are asymmetric in nature. So I just looked at what should be the similar expression for asymmetric system, where M, C, and K are not necessarily symmetric in nature. And I found out from Housie and Bishop, they have also given the decomposition of the quadratic system in a more generic form. Here Y is your left eigenvector, X your right eigenvector. And then you can generalize the orthogonality relationship. This way, remember, you know this, for symmetric system X is equal to Y. It also follows all the relationship which Dr. Datta has shown first. Now I am decomposing this system. I can decompose the eigenvalue does not change. You may have, now you will have a different left eigenvector and right eigenvector. Whenever you are calculating left eigenvector, you can take a transpose of the matrices and the right eigenvector of that transpose of the matrix, left eigenvector. If you are doing in MATLAB, I am just showing you, you can write any kind of state space form. So I wrote one of the form, symmetric form. Instead of M, C, and K, I am using M transpose, C transpose, and K transpose. So its corresponding eigenvalue will be matrix A plus lambda B equal to 0. Now, MATLAB, if I am using the I command, I A comma B, Now it will give me the eigenvectors which are left eigen. Okay? Make sense?
Yes.
You can choose. Good thing is that you can use the same form which Professor Dutta has given in the paper, calculate uh, the control gains. Only thing you need to aware when you are using the asymmetric system, that in this equation this is now a left eigenvector, not the right eigen. Okay, so you can calculate for asymmetric system left eigenvector now for your exam. Echo.
By hand or by
You can use
program?
by MATLAB. The only thing, no, use MATLAB. Don't do it by hand. I don't expect you to get a complex eigenvalues and eigenvectors by hand. Lot of time, eigenvectors can be normalized. So if you want your computation easy, you can normalize it, divide it by one value, but just use MATLAB for your calculation. Right? Now, because we have this nice formula, now we have demonstrated that no spillover will also happen for asymmetric system. Naturally, in aeroelastic problem, we have asymmetric mass damping matrices. I have taken one model from Zhao. It's basically the pitch and plunge model. It has just the different values. During that time, I was working on this problem. You have asymmetric C and K. These are the open loop eigenvalues. I took it for the case of post flutter velocity of 25 meter per second. For this particular system, the open loop flutter was at 23.5 meter per second. And then I am just moving poles to the mode which was flutter. And I kept the other mode there. And then by using that formula, I calculated the control gain, and I can repeat it for each velocity. Now you can see that the mode which is fluttering moved it without affecting other. Still got the flutter boundary extension, but it did not influences the other modes of vibration in that system. The partial assignment was extended by the method of receptance by Professor Motorseed and his students. And you look at the development of the receptance, you have a time domain system control, you can write it in a frequency domain, and then Laplace domain, and this is one state space representation of the same system, the closed loop dynamics of the system. If you multiply it by the corresponding mode shape, uh, if you multiply it by this expression, what you will get, and rearrange the system, you will get this equation for any given s equal to lambda g. Now, what does this mean? That in your control, if you want the control system to have the lambda of open loop system, then this term must go to 0. Yes? This term has controller term. If you want your control system, because this represents the dynamic of the control system, if you want the control system to have the same eigenvalue, then this is the dynamics of the open loop system, and this is the participation of closed loop dynamic. This term must be goes to 0. This term will go to 0, either this term is 0 or this term is 0. We have just seen this term, that formula. If D is orthogonal to the mode shape, that term will go to 0. So those are the two conditions, uncontrollability and unobservability. These will become the basis for designing the partial pole assignment, the method of acceptance. Actually, the formula which Dr. Datta Ram has shown, and it has been shown by Professor Moore Proceed that that formula is an observability condition. It satisfies the unobservability condition. So how to do it? So how to make this system uncontrollable for those modes which we don't want to take or place. That's the whole idea. By using the by doing the method of acceptances, we know the technique. What can we do which will ensure this condition? So the first attempt that took, they came up with a specific type of controller. This is called integral force feedback controller. This exists in practice, but it has some dynamics in it. Because of this dynamics, you can find a B is B1 and B2 such that it can become orthogonal to the mode shift. That's the main idea. Find a control distribution instead of a constant vector function which will make this, which will be orthogonal to the mode shift. So if I separate my eigenvalues and eigenvectors into two terms where sigma 1 is the poles we are placing and sigma 2 want them to remain invariant, then it will satisfy this equation which is saying that it will make the system uncontrollable for those eigenvalues and corresponding eigenvectors. So this B1 and B2 then it boils down to if I have chosen this form, how can I compute? And B1 and B2 is computed from the null space of the null space of this system, where you can take null space of this system, and this alpha basically showing you that you have a flexibility to select alpha. Once you compute the null space, you can select a specific columns from the null space, and that will, by computing the null space of this quantity, specific column of the null space will keep it. And that will ensure the system is uncontrollable for this form of control distribution vector, and they will remain invariant. We can apply that method in elastic problems. We have unsymmetric system, and in this particular case I chose velocity which is pre-fluttered, so both poles are placed. Will also work for unstable system also. It's not that for some reason I chose the example where the system, open loop system is stable. But I just wanted to demonstrate that process. When you calculate the null space, this is what you will get, the form of your control. This is your B1, this one is your B2. And then once you have that B defined, you can apply the acceptance method. Because in order to calculate the control gain, the only information I need is R of K, which is H time. And if I am using only two poles, this is a much smaller system. Because this controller, the distribution vector, is a function of S, it has its own dynamics. If you want to calculate the control gain, you will have an additional. There will be one pole which is coming from B1 plus B2 by S. So that you can calculate by expanding the state space. Then if you plot the frequency response function, this is a demonstration that for that particular speed, the red one is open loop system, the blue one is closed loop system. Move the poles, you move the poles from location 1 to location without affecting our second. Now, if you look at the linear solution for multi-input, you have seen this derivation, you have seen this discussion yesterday's lecture, we are partitioning into uh, R number of single input cases, and we can calculate this R which we need for pole placement. Now, if we want to make a partial pole assignment, what will happen? We need to impose the second condition. So one was phi times B transpose phi transpose times B is equal to 0, and the second expression was B times. Okay. We have partitioned it. This whole term has to be. So what will this bring? What will this do to our G matrix? That's the question. We have this G matrix which we are creating. What this will add? It's a very simple modification. So if you have 2n number of poles, and then you want to place, let's call it p number of poles, and then you will write this p number of equation. For rest of the poles which you don't want to place, you will write the expression. This is coming from the unobservability condition. Yes. What is this? This is the eigenvalue which you don't want to place and the corresponding eigenvalue. This is your argument. So still we need only the experimental data. Now I need a little bit more experimental data. I need to know information about some of the modes I don't want to control. Now, but for a small dimension system, the whole idea is that if you have 10 number of modes, 5 you can place which are dominant. Make sure the other 5 remains unaffected, which means you are blocking the energy transfer from the actuator. Hopefully it will not influence a much higher. Okay? So it's still a linear system of equation. It enforces condition using the eigenvalues and eigenvectors of the retained mode. And then you can solve. It's still a square system. You can solve it for the control gain. Same thing, actuator dynamics was the extension of the full state feedback case, where we have just coupled the actuator. The only thing changed there is the form of this R, which now had the actuator dynamics incorporated in it. Still need to create the, so it remains the same form. P number of poles, write the existing equation, and for rest you can add this. Here, if you know the poles of the actuator, don't want to control, and the modes of the actuator, you can put it here, and then ensure that those modes and their corresponding eigenvalues remain stable. That's what I am showing you here for the case of actuators. This is I am implementing the control for all velocity, all flight condition. What I can do, I just change the pole which was fluttering, or the mode which was fluttering, and then I showed second mode of the structure as well as actuator poles remains invariant. Yeah? Because of this, I can, when I calculate my closed loop poles for a unique control gain, even if when I solve for in a least square sense, I see that not much different. So it's trying to keep the poles unchanged, but because we are solving in a least square sense, there is some movement, but gives you a very good performance. Now you ensure that your actuator is controlled. Now, your actuator will not be influenced by the control. provided to the system. Same thing with output feedback. Our system matrices are a little bigger. Remember, you remove this term. This is a full step feedback. So you have this let's call it a P matrix, which is placing the poles. Q matrix, those poles you don't want to place, and E matrix, which what kind of measurements which are not available to you. And then you solve the entire system. That's what we have shown in the paper also, that for this E value, when I calculate the control gain for partial pole assignment, I ensure that the mode which was fluttering is controlled, the other mode remains stable. Even if the NC is greater than NM, if you are solving for least square case, then it's trying to moving the pole in the least square sense, and it is not affecting the uncontrolled pole that much also. Okay, let's take 5 minute break before I start last topic of time. Let's talk about, so we learned some tools in terms of new methods, receptance approach. Then I gave you the concept of partial pole assignment, which can be uh, which can be very useful for any dynamical system. And then the last one, which is very practical problem, is the problem of time delay. I had a discussion in the morning, the
Yes.
uh, vision-based sensors, and think about those situations. Even the small delay in a feedback loop can create a problem. So if you look at the problems of time delay, there are delay which exist in an open loop system. If you go to take a shower in the morning and if you want to put in the heat mode, it takes some time. The water to become heat. So that's kind of an open loop delay. Once it gets heated, when you turn it off, it does not have dynamics involved in it, which creates a problem. Maybe it's become too hot sometimes. But in the active control, we are dealing with a system which is dictated by a measurement, and that measurement has to be calculated using the control gear. It gives you the controlling force. You can have delay in measurement to control gain calculation, delay from control gain calculation to the actuator. So this is in closed loop setting, any dynamical system, when we are applying a closed loop uh, control, the delay can become detrimental in implementing the control uh, without making the system stable. So if you have a delay in feedback loop, you can destabilize the system. Right? Because the phase lag between, think about you're trying to, something is moving in this particular fashion. And in order to cancel, I have to apply equal and opposite force. And if there is a delay, you can come in phase two. Right? That's why small delay can create instability, that can destabilize the system. So we need to understand it. And in the literature, time delay has been classified as retarded type of time delay. If you look at your state space form, if the delay is only, if delay term is not in the higher order derivative, this is called the retarded time delay. If delay is in a higher order terms, then it's called a neutral time. These both are single time delay. Think about, you have only delay from control to actuator once you calculated the control. But you can have multiple time delay. You have multiple sensors. Every sensor can give you its own time delay, and cumulatively you have a time delay from the sensing side is tau 1, and time delay in the actuation side, you have multiple actuators can be tau 2. Now, what's the property of these delay systems? So let's look at a very simple first order system. If you look at this differential equation, if you take its Laplace, you will have that expression, and the poles of the system is, if tau is 0, you have stable, and you can see for any tau which is a positive number, the system will be stable. Let's look at the other system where now we have the delay in the its derivative. Again, we take its Laplace transform, its characteristic roots are the poles of the system. If tau equal to 0, the system is stable. But if tau is not 0, the system becomes unstable. More system, it's again neutral type of a system. Without delay, it's stable, and with delay also stable. So the bottom line is that any kind of system which has delay in it has infinite spectrum, which can be stable or unstable. So stability of time delay system is very critical, very important. Even if you solve a problem which involves delay, you must evaluate its stability because it has infinite number of eigenvalues. So time delay can be unavoidable for active control implementation, and it leads to sometimes quasi-polynomial or transcendental eigenvalue problem. Okay? So let's suppose now we have a control in which we have a fixed delay of tau. So if I have controller as tau, which I'm assuming that it has delay in x and x tau. Is it a neutral system or retarded?
It's a retarded system, no, sir. You know higher order terms is will.
Does-
Retarded system, when higher order term is not present.
Retarded has no higher order term.
But here is no time delay higher order term, only b of u of t minus tau. It is retarded system.
Retarded because the state vector is x and x dot. When you write in a state space form, that is that has x and x dot. Okay. But I am showing you in a physical quadratic form. Transfer into state space. So it's a retarded type of system. Once you substitute it back, this is its eigenvalue problem. Or you have to find the roots of the eigenvalue characteristic. This is the correct equation. equation. Now, because of this exponential term here, you can have infinite eigenvalues for the system. If the exponential term is 0, then we have a finite number of eigenvalues. Let's know how to solve it, such problems. So I did this in 2009 with the help of a math student, and I took the ideas from the partial pole assignment and I tried to incorporate delay. And then we figure it out that it's a small modification to the partial pole assignment problem. So we have MCK and the control distribution, and then we have a fixed value of tau. We wanted to have this system has this open loop value of 2n. We wanted to change m number of poles and keep 2m number of poles. So we want to move lambda 1 to lambda m, to mu1 to mu m, and retain lambda m plus 1. We want to find f and g such that it will satisfy this discriminant equation. If I satisfy this, I made the case that the pole placement has been done. So I will again use the same tool which we use for partial pole assignment. One thing always remember, partial pole assignment is the generalization of a full feedback control or full pole assignment. If m is equal to 2n, we are moving all the poles. So we use the same the expansion or decomposition of the quadratic eigenvalue problem. No properties of some of the orthogonal properties. We separate them into poles we want to place and poles we want to keep, and then we'll use the same form of the control gains. We want to show that if I choose the same form of the control gain, I am just distinguishing Q2, the Q which you have seen for which the explicit formula we have just seen. I want to first show that if this is the case, then this will also have no spin. And that can be done the same way which we did when we did not have any time. So if you follow the same process, you will say that you can show that time delay term does not influence this diagonal property, diagonal orthogonal properties, and it will ensure that still it will make time. So you, with the same form of the controller gains, you can have no spillover. Now the next one is that we don't know how to calculate the Q as the explicit form, but that is only valid when there is no delay. So Professor Datta in his earlier work has also shown a numerical method how to solve for a situation when you don't have explicit solution. So we chose the same strategy. So the idea is that if there is a beta exists such that you are able to ensure no spillover, there will exist an eigenvector which will satisfy this equation. So he has an expression where this term was not there. He has shown the proof. We follow the proof, and we are sure that it will also be valid for time delay. It's rather lengthy derivation, so I'm not showing you. Where D is the matrix, diagonal matrix consisting all the D poles. You can calculate the exponential matrix corresponding to that, and then you can rewrite this equation into left hand side this term and right hand side this term. So it's a matter of solving a linear system. And he has shown that if you choose C to be unity vector, you should be able to solve for the beta. And if you want to solve for the y, the element of y, which satisfies this equation, it can be solved by this equation. So once I computed zeta, I can calculate beta because C is known to us. So sorry, once I calculated Z, I can calculate beta with the C as the vector consisting of ones, and then I can calculate the vector. I just want to reiterate this formula is valid when there is no time. And then we can do a numerical experiment. I took a symmetric system, MC and K. I chose time delay of 0.01, and then I have two poles I want to place and preserve the third and fourth pole. I can construct the matrix X, which is these are the two eigenvalues. These are the corresponding eigenvectors. Talk about partition. You can solve for Z and then beta. So right now we are not doing the stability analysis. We just want to ensure that where we are able to do the pole placement or not. And one way we ensure that determinant goes to 0. So just to accuracy, find out that it's going to 0. And then we can look at the various aspects of it, and this is something important. Even if you find the literature, basically the idea is, can you exploit time to minimize the controller loss? So what I'm just showing you that for this particular case, for different time delay, you have a lot of variation in controller gains. But the most important thing is we need to do some kind of stability analysis, some post-stability analysis. Okay, I have shown that even with the inclusion of time delay, I can do partial pole placement successfully. But I don't know whether the system is stable or not. I know those poles which I have placed are stable. Those poles I retained are stable. So the extra poles which is coming from the power tau term, the fact it's infinite spectrum, I don't know whether they are stable or not. So that's the most important aspect of time problem. And people have come up with different ways to do it. That's what we don't know what is the unknown poles of the closed loop system. One of the simplest way I've seen is that you can expand this eigenvalue problem. It's kind of a non-linear eigenvalue problem, or I call it a transcendental eigenvalue problem. During my dissertation, I have a numerical method I developed for transcendental eigenvalue problem. So I can solve for a lot of roots, but I don't know whether, and I can solve near the imaginary axis. What are the roots? Make sure it's stable or not. But there may be one root which is much away in the right hand side. So it boils down to what's the space in the complex plane and whether you are capturing the roots which potentially become, where you're capturing the domain which has unstable root or not. So the other way to do it, that you can expand this nonlinear eigenvalue problem by Taylor series expansion and then look at the finite number of roots. You can do higher order expansion of Taylor series. But still, you will get some idea that near the imaginary axis, you can find out whether the system is stable or not, but not necessarily the entire spectrum, not guaranteed. This is just a demonstration that you can find out the primary eigenvalues of the closed loop system, which are closer to the primary axis. Now, for the case of multi-input, this concept of partial pole assignment will be extended. It's a very similar way what we did for the partial pole assignment without time delay. Process remains the same. I have the same partition of the eigenvalues and eigenvectors. I have done both for symmetric system as well as asymmetric system. So you can have inclusion of left and right eigenvectors also. Once you do for asymmetric system, the symmetric system is uh, when x is equal to 1. So in multi-input case, if you have an open loop system, we have 2n eigenvalues with the definition of our controller. If you remember the term beta, which we use for the single input case in partial pole assignment, this beta is replaced by the vector is replaced by a matrix. So it can be shown that if your control matrices are of this form, then there will be no spillover. And we can prove the entire thing in a similar way. This is for the case when the system is symmetric. We can do the same exercise for the case when the system is asymmetric. Okay? So the idea is that with the similar form, by replacing this vector matrix, you can ensure that there will be no spillover. Now, the way we calculated the gains for the single input case, this process, we will follow the same one, calculate for h. So apart from the fact that delay introduces these concepts, the matrices, everything. So if you look at a multi-input case with time delay, this is the work I've done with Dr. Rajiv Day. He helped me to, he's the stability guy. I was the partial pole guy. So this is our work with Professor Datta. So we have a multi-degree of freedom system with the multi-input case with a constant time delay of 0.1. We wanted to retain the first two, we wanted to move the first two pole to new values and retain the other four poles in the system. Then from our definition, these are the eigenvalues and corresponding eigenvectors. I can calculate D and the exponential matrix which we computed for control gains. And then by, if you recall, we choose C is equal to 1. Here you can choose, it can be arbitrarily scaled. So we chose gamma to be two values and then solve for C and then H. Now I have it. So I have a controller gain for a multi-input case with time delay. We can check it and it's place the pole. Now by that time I have developed an algorithm from the transcendental eigenvalue problem, and I have a tool to calculate the spectrum of a closed loop system. So some of the closed loop numerical tools we have, which I am listing it here. First one is developed by me. The second one, Taylor series expansion, and the third one is a more robust tool, the MATLAB toolbox, which is called TraceDB. But it does that if you input if you have to convert everything to state space. But if you input your right A, B, and tau, it gives you the spectrum for a range in the imaginary and complex. This is how it looks like. Okay? So these are the two poles. Those these are the poles we obtained. Then there are so many other poles in the system. In this toolbox, you can say how many poles you want to see, what range you want to see. So it does that calculation for you. This is the spectrum. So seems like it's a stable system for dipole. The second case where we move four poles and retain two of them. Okay? Place four poles, new locations, and then retain. Then I use trace DB to compute this. So now this spectrum is different. So it tells you that this spectrum will change what kind of tau you are choosing and what kind of pole placement you are choosing. So it's not a constant spectrum, but you make changes in the closed loop system. One way to do it, I do this exercise for all possible tau and find out whether it becomes stable or not. But luckily, we have some numerical tool available to evaluate the stability of the system. But some of the numerical tools there are, if you want to have list of uh, the numerical methods or solution strategy to find the stability of a time domain and stability of a time delay system in time or frequency domain. This is a very book. The most commonly used, which has gained recognition in I believe last 15 years, Raji, 2002 was Sipahi, this paper, 17, almost 20 years. So CTCR, and I also like it's a very simple method, but it is slower. By so let me hand it to Professor Day. He will talk about CTCR, then I will talk how our solution. Why don't you talk about what CTCR is, why it's capable of finding out the stability domain?
I'll be very quick in explaining the technique. It's very simple. Uh, Developed by R.C. Pahi in 2002. You have seen CTCR. I met him personally. And this is the work that we collaborated in 2012 with Professor Datta and Professor C. So this is how we went into friendship. So this work was done by BTech student, undergrad, 2010. And later on, it got publicized. And through that, Datta contacted me and he wanted posterior analysis of partial pole assignment, for which his paper that got published in 2014 for 7 years, it was not published because there was no analytical framework to prove that the way they are placing the pole for a particular gain and a delay, they could not prove mathematically that whatever choice they are doing analytically, they could not prove that is correct. So we met in one conference and he said, I have gone through your work and we want you to work on the problem that we have. We'll supply you all state space A, B matrix. The rest, you try to give us an analysis for the value of K tau that we have chosen and done our partial pole placement. So my work is only posterior stability analysis. So I'm not going into the work that got published in 2014, but the work that was done by an undergrad. And this work was awarded by Indian National Academy of Engineers as the best BTech Innovative Award in 2010. So the problem that we solved is like this. This was the motivation, and we took It will run. Run video. Action.
Which video is that?
Don't know what. There you have.
You can do it.
Yes. No, there is no internet. Okay, forget it. So this was the motivation of the problem. The video is not there. So when a crane moves, a tower crane moves, there is a lot of sway. There's a lot of vibration, and that's does not define the safety of a factory. Because when a big crane moves in a factory environment, and it sways a lot. So there comes the control application. So by using some sort of control, can you damp down the oscillation of the payload, right? So it enhances your safety, the production time. So that was the motivation of the problem. So that's a gantry crane problem that we have done. So I'm not going into it. We have modeling concept. We have used Lagrangian, got nonlinear model. We linearized because we want to have a very less way. So these are state space formulation. We have been doing it for last 5 days on aeroelastic problem. So it is similar type of mechanical system where you will get MC, may not be K here, but M matrix, C matrix, later boiling it down into your state space formulation. So we did open loop simulation. You can see that system is highly oscillator. So it means as the crane moves with certain velocity, it sways a lot, and you want to damp down. That's the problem. So you can see these are something parameters that we have captured, and we did some pole placement controller using place command because they were under dread. We don't. So this pole placement problem, you have been doing it for last 5 days. Now you know how it works. So we did it using place. So these were some results. We placed the poles, we calculated gain, and we could, using pole placements, also damp down the swing. Then we tried for LQR, worked, but the gain matrix was coming very, very high. Then we tried to devise a method which is called output delay feedback. So what we did is, there is no delay in the system. It is x dot equal to a of x plus b of k, p of u. What we did is, we substituted in the feedback a delay term. So it was something like ut equal to k x t minus tau. So in the feedback, as Professor Singh was saying, that in the feedback you can have a devastating effect. What I said is you can have a good effect. So you can now very clearly understand how did I get this equation. The system is non-delayed. The control input u equal to k of xt minus tau. If you substitute, you will get this equation. Not in under closed loop. So now finally you get a system which looks like x dot equal to a naught x a1 xt minus tau. Right? This is what in state space is called retarded time delay system. You don't have a delay in the higher derivative. Right? In the non-derivative state, you have the delay. So it's a retarded system that Professor Singh said. So if you find the characteristic equation of this, it comes something like this. You do the expansion of this characteristic equation. So now you can see that you have a term. This is what it makes this characteristic equation transcendental, and it's an infinite dimensional system now. It's no more a finite dimensional system. So because e to the power minus s tau, for any value of s, you will have as many infinite number of roots that will satisfy this characteristic. Right? So any infinite dimensional mathematics, it's very hard to solve using finite dimensional mathematics. So you need to use certain trick where an infinite dimensional maths can be solved using finite dimensional mathematics. So that's the challenge. Characteristic equation, if it's deterministic, it's finite dimension, you can find the roots, finite roots. use Routh-Harvigian criteria, whatnot for finite dimension. The beauty of CTCR is how Sipahi used Routh-Harvigian for finite dimension system. That's the catch here. So very shortly, I am going into CTCR. CTCR stands for cluster treatment of characteristic roots. So what they do is, in this equation, they will replace the star by certain substitution, which is called Recasius substitution. So they will replace e to the power minus s tau by a pseudo delay parameter capital T. And the mapping between e to the power minus s tau equal to pseudo delay parameter capital T, which you see on the right hand side, this mapping is exact. This mapping between tau and capital T is exact. So now if you replace in this equation this star on the right hand side, now it will become a characteristic equation free from delay, and it will become finite dimension in the parameter capital T. That's the beauty. As soon as it becomes a characteristic equation in a variable capital T, you can use Routh-Harvigian, right? So you can formulate a Routh-Serre from an equation which is a function of capital T, not now using this pseudo delay parameter, the technique says how will you extract the value of capital T from capital T, the value of omega, the frequency, and the delay. So now it's very easy to understand, you can see. So one more thing to tell here is the philosophy here is we have said when you have e to the power minus s tau, you have infinite roots. And the disadvantages has already been explained by Professor Singh. How many roots will you find? How many spectrum will you see? Right? But there is one certain property. There will be some finite number of roots that will lie on the imaginary axis. Right? So instead of computing infinite roots, try to detect only those roots which lie on axis. That's the philosophy. And this paper of Sipahi got published when he was in BTech. In his, he is from Turkey. You met. I also met him. So that was his philosophy. So this you can see that Routh-Serre formulation is done at s equal to plus minus j omega. So he is only trying to detect finite number of roots on the imaginary axis. So if you now detect finite number of roots on imaginary axis, that's not enough, right? Now there may be tendency for some roots to spill over to right hand side or to the left hand side, right? So now what he did, he tried to compute something called tendency of the roots to spill over to right or to the. That was his main contribution in the paper that you referred. So we formulated a Routh-Serre. Now you can see they are parameters of capital T. You know this is the necessary condition for marginal stability case, right? So if you solve this, because T is a variable, now if you solve this, what you will get? This will be the auxiliary polynomial. You know that, Routh-Serre. So simple. So if you solve these values, so you will get the values of from T, you know the value of omega. From omega you can calculate tau by this relation. This is called continuity theorem, right? Because it's a periodic solution, basically e to the power minus j omega tau. It will have some solution which is periodic, right? So this is the type of solution it gives from these two equations. If you solve, if you know T, you can compute omega. Those are called critical frequencies, and for those critical frequencies you can compute the cluster of these taus, right? Now you know the crossing frequency, omega tau, the crossing frequencies you know, right? Now the only thing that you have to detect is which of the roots lying on imaginary axis, various omegas, which roots will have a tendency to go to right and which will have a tendency to come to. That's the only thing that you have to do. I'm not going into formula. So first you find all the critical values of delay. These are the critical values of delay which you have computed. This is the formula that they use. It's a very simple formula to compute. Once you know the critical values of delay, you have to find the tendency, root tendency. It's nothing, very simple thing. It is root sensitivity. How will you find root sensitivity? ds by d tau. As tau changes, what is the tendency of the root to move? To left half or right half? So it is ds by d tau at s equal to plus minus j omega c. Right? And the most important investigation they did is that they found that those which crossovers, those who have a tendency to go to the right hand side, they all yield a sign which is plus 1. So how they found out a sign convention? It is something like ds by d tau at s equal to something you calculated. Now you take the real part and put a sign test to that at s equal to plus minus j omega k, because omega c you have already computed. If it comes as plus 1, they found that it crosses over to right hand. If it is minus 1, comes to, that's it. Very simple. So once you find this root tendency by this formula, then they arrange these roots, these tau values, by looking at the plus 1 or minus 1, the signs, right, for particular value of frequency, and then from there they make a chart, because tau m0, tau m1, tau 20, they will have different values. So you arrange them in ascending order, check their signs, and then you can decide. So a chart something like this is made. So all the values of the delays are arranged, then they check their root tendency plus 1, minus 1. So now they can decide in which interval, say from 0 to, in this the problem that we consider, the problem that I have shown you, from 0 to 0.498, it is showing plus 1. At 0.498, it is showing plus 1. It means from tau equal to 0, less than 0.498, sign was minus 1. Exactly at 0.498, it gave a value plus 1. Means at this value of delay, 2 roots has gone to right hand side. So at 0.498, the system becomes unstable. Right? So it is detected. Now you see, when you go from 0.498 to 1.0046, at exactly 1.0046, you find a sign of minus. Means what? Again, after 1.0046, system becomes stable again. This is what is called the peculiar behavior of delay. A non-delay system does not behave like this. It's very easy to detect instability. But this, in some pocket, you are finding the system is unstable. Again, you are increasing the delay, you are finding it becomes stable. Again, in some pocket, it's becoming unstable. This is what is called switching of stability. Stability switches in a time delay system, right? And detecting it, people have used graphical techniques, numerical techniques, but there were no analytical framework. So the CTCR is an elegant framework to solve this. So you can see the switches now, critical delay values, as well as their root tendencies. So now you can very easily say from 0 to something less than this, it was stable, again unstable, from here to here. From after this, again it becomes a stable, again unstable, unstable, again stable, and again unstable, and thereafter unstable. Right? So you can see I have checked for tau equal to 0.2 simulation for the time delay system. So what happened? I have kept a gain equal to 10 in case of Professor Singh. the gains are calculated by his partial pole assignment problem for a particular value of tau. What I was supposed to tell him is an analytical method that whatever stability pocket I find out is exactly matches with him, and it matched. And this work actually shows us. So if I take a delay of 0.2, it means it is less than 0.498. System should be stable. So simulation shows it is stable. Right? Next, I consider exactly delay value 0.498. So it is marginally stable on the margin. You can see it is marginally stable. Now I consider a value 0.52. In this range, it should be unstable. The chart says so. So it is unstable. So I have tested for all the pockets and it came exactly correct. That's what was our collaboration. But my student did this. These are some calculations. What I want to show you is nice video. I don't know video will run. Not. We did it in an experimental setup. And now you can see it's not more. This is not online. Yeah. So here the control is on. You can see the velocity with which the train was moving, but still the sway was almost negligible. I play it again for you. You can see the swing. It's almost negligible because at this velocity will swing a lot because it's a highly oscillatory system. The control was on, and it's a tracking problem. Who are playing? Who am I? It is all. Okay, anyway, let me show you now. It's a tracking problem. We have given a sine wave. It's tracking as well as it is suppressing the vibration. So it was, you can see this is the 0 mark. So it's coming here, going there. So it's a sine wave track. As well as the suppression also you can see that there is no sway. Control is off here, and you can just see the graph of tracking that we got. So you can see that this is the vibration or the sway, this is the error, and this is the tracking sine wave that it was tracking, and the vibration was captured here. It is 10 to the power minus 10 scale. So that's the use of CTCR that we did, and after that, that's the very simple. Thank you.
So now you know a technique to find the stability domain for a time delay system. In our case, we have calculated the control gain. For that control gain and time delay, which is a constant, system was stable because that's how we chose to. However, in practice, what can happen that we have assumed one delay, one value of delay, but we cannot definitely say that how much delay is coming from sensor A, sensor B. So these delays can change. So even if you fix that, okay, this control gain is fine for my pole placement, we need to know what will happen if the delay changes for the same control. So I handed over to Professor Day, and he give me the stability switches. Okay? So he did the UTCR method, and he found out the domain of the tau for which the system will be stable, and those domains which will be unstable. So now I can go ahead and check, like he was showing you, whether within this with these tau values our system is stable or not. So if I took tau to be 0.6 in this domain, this one is open loop system and one is closed loop system. So stable, and I take 1.1 unstable region, system become unstable. Sorry, it's not open loop or closed loop. Sorry, let me take it back. This is the tau which we originally designed our controller for, which the system is stable because it shows the pole. This so one way to look at it, that if I have the pole placement, yes, and my closed loop poles show that the system is dying this fast. Because that pole placement varies, maybe if I change the tau 1, it will go faster with the same. But for other tau, it becomes unstable. So for the fixed controller gain, I can either decide make it perform better and make sure that it does not stay. This was the idea. I did this analysis for aeroelastic problem, also for the flutter problem, and this is just I'm showing you a open and closed loop flutter. You can directly say the partial pole assignment without affecting these modes, and lot of other rules which is getting the system for different velocity. This is also quite interesting that once you fix once we have a process to calculate the control gain for different velocity, you can look at its dependency for each velocity time delay in terms of the controller norm. What it simply says that for a given velocity, given flight envelope, you can introduce a tau to minimize the controller norm. Make sense? So control gains are influenced by the time delay in the system. What Razi was saying that for the gantry control, introduce the time delay to take advantage of the delay. Vibration also, there is something called delay resonators, which try to exploit the delay to improve the performance. So the video you saw, let me ask you, what is one of its eigenvalue? 2 degree of freedom system, one mass, then pendulum. You should know it's one eigenvalue. It's rigid body mode. See, at the top mass was not constrained, so the whole system can move as a rigid body. We have done that rigid body mode problem. The system is not constrained. One of its mode is whole system acts like a rigid body. So one eigenvalue is 0. Second one, oscillation of the sway being controlled. Okay, so last thing, what happens if you have a receptance method? You want to do. So let's look at the same time delay problem. This is, you have an exponential term due to the time delay in the frequency domain, and we can rewrite my closed loop receptance in terms of open loop receptance, and it will involve this exponential term. The roots of this term has to be 0 in order to calculate the controller gain. If you rearrange it instead of 1, you will get this expression. Now for a given value of tau, You can easily calculate the time. And this is not only for one control. Even if you have two delays, when I was preparing the slide, I remember last year we were working on two delay problem. I figured it out, the receptance matrix for that, and he has to do now stability analysis for two. So if you have two delay, let's suppose you have a different delay in the displacement sensors and another delay in the velocity sensor, you can incorporate that in formulation. And if you look at the expression, you have. And you can have for acceleration also, we have the output feedback case where we have used the redundancy of acceleration. I can expand it and also and incorporate up to 3D. Now, the only thing is I am assuming same type of sensor will have same type of delay. So if you are interested in working on or analyzing stability, feel free to join us. I have the solution, and I'm looking for someone who is interested to do stability analysis of such problem. Okay. Any questions? Enough of me? So what I am going to do that I have a video. So I want to tell something about my university. You have been, I am talking to you for